So I heard you guys all saying the right things. How do you know? You came up with something I actually didn't think about, and someone said something about concavity, and that's another way to know. Nice job. That whenever the function is concave up, the rate of change is increasing. Whenever the function is concave down, like a logarithmic, the rate of change is decreasing. So f is definitely growing at a faster rate. And so, did anyone figure out 4 without me telling you?
We said it's
Or
0.
you heard me say 0?
Oh,
No, we
let's
did.
go, Mama Grace.
Well,
I
You
told
did it?
you.
What we did was we knew after they intersected, the denominator would keep increasing.
Yes. And so the denominator is growing faster. It actually dominates. And we talked about this slightly last year. All right, and then, so this, whatever, it's not really called a name, but when we take G and divide it by F, is getting smaller and smaller. As X, I'm just going to say approaches infinity, as X increases, those values are going to get smaller and smaller and smaller because you're dividing by a bigger and bigger and bigger number. So eventually you end up with 0 because you're dividing by something so big. It makes it non-existent, basically. Okay, not really non-existent. It makes it 0. Okay, so then we have this one where we plug in 3 to each of those and we got 0. And so that means that whenever we plug into this limit, it is going to give you 0 over 0. Do you guys remember what that's called? It's a type of form. It starts with the I. Indeterminate form. All right, so remember, with indeterminate form, there is a limit. You just have to do something to find it. And so what we did before, because we didn't know about this new rule, because we didn't know about derivatives yet, is one of the things we would do would be to factor the numerator and denominator. And that will still work. Like if factoring is your favorite thing, and it ends up being a polynomial over a polynomial, you can still do it. But I think you're gonna like this new way better. So the x minus 3's cancel, and then what do? Yeah, you plug this 3 in here, and you get 8. All right, and then A says, how do the values of f of x and g of x at 3 compare? We already knew that. They're both 0. And then which function is changing at a faster rate at 3? Yeah, we could find the rates at which they are changing. And then when we plug in 3, oops, is it F? It's going to be 6 plus 2, or 8. We plug in 3 to g prime, obviously, this is just going to be 1. So f of x is changing faster. And then you've got evidence over there, that's how you know. Right? And then if I want to do the limit as x approaches 3 of the primes we just found, right, we've already plugged 3 into f prime and got 8. And I plug 3 or anything into g prime, I get 1. So what do you know about, or what do you notice about that way and then the way we did before by factoring? They're the same. So that's the new way we can do it. We can, and it's very limited when we can use this rule, but if we can compare the growth rates when we evaluate the limit, and it's only when direct substitution leads to indeterminate form. And there's different ways we can get indeterminate form, and we'll write it on the other side. 0 over 0 is one of the ways, but also infinity over infinity is one of the ways to get indeterminate form. All right, so this new rule is this. It looks like L Hospital. If that's why this shirt is funny, because I'll send you, or you'll have to go to the hospital. But this guy is French, so who took French? Liam, do you know how to say that?
Yes.
How do you say it? Do you want to share?
L'hôpital.
Yeah, l'hôpital. And so that is his rule, l'hôpital's rule. If you use it on the AP test to do a limit, you do need to say by l'hôpital's rule. If you forget how to spell it, think L Hospital. Everybody knows how to spell hospital. All right, and so you can use this rule whenever you get 0 over 0 or infinity over infinity plus 2, because those plus 2 are indeterminate.
Are you recording?
I am. Do you want me to pause it?
No.
Okay. All right, when that happens, we can consider the ratio of the growth rates instead, or the derivatives. All right, so when the limit as x approaches a of f of x over g of x is indeterminate, you're going to evaluate the limit as x approaches a of f prime of x over g prime of x. So you'll just find the derivative of the numerator and denominator and then plug that in. Sometimes it gives you indeterminate form again, and it's fine. Then you can just find the derivative again, so you can repeat the process as many times as you need to. So if the result is still indeterminate, repeat the process to find another derivative. And that happens some, especially on polynomial functions. But we can do this for all kinds of functions, which is what I have on my examples. All right, so on number 1, we want to find these limits. So first, we do need to plug in the zeros and see if we get 0 over 0. You don't ever, and I know I told you this before, do not say the limit equals 0 over 0, please. It equals something totally different. So what you do is you just draw like a little arrow to show what you get in the numerator and what you get in the denominator. So when I plug 0 in, and I get e to the 0, what is that? And then subtract 1, 0. What about the sign of 0? So this is indeterminate form, which means we can do L'Hopital's rule. All right, so what is the derivative of the numerator? Yes. What is the derivative of the denominator? Nice job. All right, so here we go again. We can plug in the 0 for each x. We just said a second ago, e to the 0 is 1. What about cosine of 0? Also 1. So the value of that limit, the original limit, and the one where we did the derivatives is 1. Now, if you did this on the free response part, you would have to say by L'Hopital's rule to show them you know what you're doing. Okay, so let's look at number 2. So at this time, we are going to plug in 7. It's a little bit more difficult to do in a head, so it's going to be 49. Negative 7, sorry, I need to put my glasses on. It's still 49 minus 70 plus 21. 0. All right, and then the denominator is 0 minus 49, which So we can do L'Hopital's rule. Okay, then I will plug in -7. Goodness. Alright, so I'm going to get 2/7.
Could you have like done that factor and so we can see what's wrong?
If you like factoring better, it's fine. You also, and I was going to talk about this at the, just kidding, no. Our only option on this one, sorry, with -7 is factoring. Or L'Hopital's rule. Same thing on number 3. If you want to factor that.
So I'm not gonna do it like that.
Okay. Well, you would factor out a common factor. It's really not too bad. But let's do it. Since we're practicing L'Hopital's rule, I'm going to do it by that way. And this one I wanted to show you anyway. Okay, so I'm going to do the derivative of the numerator. Over the denominator. Alright, what happens when I put in 0? You still get indeterminate form. You still get 0/0. But that's okay. Then we'll just do the derivative again. Right, and then this time I get -12 over -10 or 6/5. All right, now I know you guys know the AP people love these tables where you have some values of a function and derivative of multiple functions. So this one we have f and g and their derivatives, and the only thing we're worried about is that when the x is 3. And so if we evaluate this original limit at 3, I'm going to put 3 in for x. And so f of 3 is 2, so then I get 6 minus 6 or 0. And then g of 3 is -1. Alright, so I do get indeterminate form. Alright, so really, my only option, I'm trying to think of any other way I could do this. I can't think of a way. My only option is to do L'Hopital's rule. And it feels weird because table values, but we can still do it. So if I find the derivative of x times f of x, what rule am I going to have to use? Product rule. So I'm going to leave x alone. Whoops. Multiply by the derivative of f of x plus leave f of x alone. Multiply by the derivative of x. Do I need to worry about that -6 when I find the derivative? Alright, and then same thing in the denominator. I would do g prime of x, but I don't need to worry about 1. Alright, so now I can just do direct substitution with the 3. Alright, so looks like we're going to end up with -5/2. Alright, and then let's do this last one. So this one, x is approaching infinity. And so if I take infinity and square it and do all this stuff to it, I'm still going to get infinity over infinity, which is indeterminate form. So I can find the derivatives of the numerator and denominator. All right, looks like that's still going to be infinity over infinity. So I can find the derivatives again. So that is going to be a limit of 3/5. All right. So do you guys remember what you actually find when you're finding the limit as x approaches infinity? In this case, it is a horizontal asymptote. But yeah, it's the end behavior. Do you remember how to find the horizontal asymptote of a rational function without doing a limit or derivative? You don't have to factor it for a horizontal asymptote. You compare the degrees. And so if you guys notice, the degrees are the same. So how would you do the horizontal asymptote? 3/5, which is that. That's the absolute fastest way to do that one. That is how I always do. If it's polynomial over polynomial and it's infinity, I always do horizontal asymptote, but that is like embedded into my brain forever. You guys haven't done it obviously as much as I did. So I'm gonna write a big or when approaching infinity. Or negative infinity, you can find the horizontal asymptote, if there is one. Which does end up being. Do you guys remember what the horizontal asymptote would be if the denominator has a larger degree? Yes. What about the numerator? There's not one. You guys are so smart. All right, I'm going to give you all your worksheets.